sessions feeling like you understand what machine learning is all about, how it's being used by Google, and how you could actually build your own neural network, deep learning network, if you wanted to. And we'll touch on a little bit of how you can use these tools in the cloud as well. It's quite a bit of material to cover. How many people here have done Python programming or familiar with Python? For those who aren't as familiar, this is a great resource. It's a pretty short book that gives a nice kind of, as it's titled, whirlwind tour of Python programming. I recommend that. This is the agenda. In this session, I'm going to try to go through some foundational elements and talk a little bit about what a neural network actually is and how it works. So let's go over some foundational concepts. Have worked with machine learning. Okay, so would consider yourself a practitioner, perhaps. And how many people feel like they know what it is, what it's all about? Most people, but we'll do a little bit of background to make sure. So this sentence is famous because it has every letter of all 26 letters of the English alphabet in one sentence, but I've tweaked it. It's usually stated as the quick brown fox, and I made it the brown quick fox. And it's wrong. It's actually not just sounds wrong, it's actually grammatically incorrect English. It's hard to do these audience challenges in this kind of distributed space, but the reason it's wrong, these rules about the order in which we arrange adjectives in English. So quick is a quality and brown is a color. So we say quick brown. So if I said look at that big red car, I wouldn't say look at that red big car. It just sounds wrong. So we all have these, native English speakers I should say, all have these ideas about how to say things, but we don't all know people knew these rules. In a way, no one knows them, but in a way, everyone knows them because you've internalized them. And so there's this interesting phenomenon where you know things. You know red big car sounds wrong. So you do in some sense, but you don't consciously know them. So how is it that you've come to know things that you don't even know you know? And the reason is through pattern exposure. You've been exposed over and over throughout your red, and you've never heard red big, except in this talk, hopefully. And so you just start to pick up these patterns by exposure, and that's really what machine learning is all about. It's learning from rules we still have, but on top of the rules, we're adding experience. If you've ever taught someone to play chess, as I did, this is my daughter many years ago, the way you do it is you teach them the rules. How the bishop moves, here's how the pawns move, here's how you do check the opponent's king, and so on. And after they learn the rules, they're like, okay, what do I do now? And the answer is kind of like, well, you have to just play games. And the playing of games over and over again is how you start to really learn what's going on in chess. So again, that's how humans learn chess, and that's what machine learning is all about. We're writing software to learn in that we're teaching people. So this idea is actually not a new one. A long time ago, back in 1950, actually, someone wrote this. Instead of trying to produce a program to simulate the adult mind, rather try to produce one which simulates the child. This was said in 1950 by Alan Turing in a famous paper on artificial intelligence. And that's, again, another way of thinking about it. So interesting that this idea was people were becoming aware of this idea 70 years ago. So if that's the case, why did it take so long for it to germinate and become the phenomenon in the last 15, 20 years? And the reason I would argue is that there's been a revolution across many dimensions of technology. Hardware has gotten better and better. That's not a new thing. Moore's law has been has been at work for that entire 70 years, but it's continued to progress, and we've had a new generation of special purpose hardware called GPUs, which are very good for the type of analysis, the type of mathematics we need to do in these deep learning networks. Cloud computing is a relatively recent thing on the scale of, from the 50s till now. It's been a powerful thing for the last ish, and it's made it possible that the average person can do things that you could never do before. It used to be when I started my career, if I wanted to do some kind of very intense computation, required 1,000 or maybe even 10,000 processors. The only way that was going to happen is if I worked for a big company and they let me have access to that stuff. Now you can actually rent 1,000 computers, and it's not that expensive if you don't use it for too long. There's more data available now than ever before, and the advent of the web in the 90s has made that, and then applications on top of that like GitHub and source, it's made all that data so much more available. So there's more data at your fingertips now than anyone's ever had in history. GitHub and open source I already mentioned, and then there are new algorithms that have been produced that are game. A lot of these things feed on each other. More computing power, you can try new algorithms faster. And so we have what's kind of like been a perfect storm of all these factors. Just mention for a minute because these terms AI, ML, and deep learning get kind of thrown around quite readily nowadays. I tried to put this into not only a Venn diagram kind of context, but also so as I mentioned, Turing and other scientists have been talking about artificial intelligence, which I think of as the science of trying to get machines to think and to do automatic tasks that typically would have required a human intelligence. Been talking about that since the 50s. In the 80s and beyond, this technique of machine learning started to come into the fore, where we're now trying to get software to learn the same way we do teach humans to learn. Learning has been really the biggest breakthrough of all. It's a way of building neural networks to produce machine learning software that's turned out to be very powerful and very effective. That's really what we're going to focus on today. There have been a lot of breakthroughs. I'm going to kind of gloss over this, but software now recognizes objects and images with higher accuracy, higher fidelity than humans. Level, I would say actually at human level, handwriting transcription, incredible advances in machine translations. All of these breakthroughs have been due to deep learning, innovations in deep variants of machine learning in the last 10 to 15 years. So we're really at an inflection point in technology. This is a great resource. By the way, these slides have sort of Easter. Click on the images and go to the articles. This is a really nice article by the New York Times, which profiled the Google Translate team as they were introducing deep learning into their product. And it was actually quite a dramatic story because the engineers responsible for Google Translate started out kind of skeptical because they'd been working on these hand-tuned statistical models. I think they had 150 different models for pairs at the time. And they'd been, some of them had made it their life's work. And it seemed a little hard to believe that that could be, renovated or reinvented by the technology that was being proposed. And what they found was that they actually were able to deliver the machine learning-based, the neural network-based version of Google Translate much faster than anyone anticipated originally. And the quality improvement was just incredible. It was better than anything they'd been able to achieve with their previous models in the past 5 years in sort of an overnight, cut to production of the new model. When they were done, they ended up with one model instead of 150. So they'd built something that really kind of fundamentally understood language in a very deep sense that could translate from any of those 150 languages to any other. So it's quite a dramatic story. Interesting sort of snapshot in the history of the development of this technology. If you look at the papers that have been published about machine learning every year, you see this exponential curve. That's kind of a clue that something's been going on. This is a graph of the number of machine learning models in the Google source repository. Google famously has one gigantic repo, as it's called. And this is the prevalence of machine learning models in that repo. And you're seeing that same adoption curve with exponential growth. Pretty much every product Google has is using this technology, not just as a feature or some peripheral kind of capability, but as a core capability. So the next little section talks about different learning. So this is a really nice article, and if you click through on this image, you can read it at your leisure. But it shares a taxonomy of all of the different types of machine learning approaches and model types. And it's kind of a zoo, right? There's a lot of stuff you can do in this domain. There's no one solution. So I've got some interactive things you can click on here to learn more about some of the techniques, like decision trees. This is kind of cool. Reinforcement learning is a technology where we teach an agent with no initial conditions, no initial information, how to learn to do something that typically a human would be good at, but we wouldn't expect software to do. And we've seen great advances in this technology. For example, the Alphago Zero initiative, which produced the most sophisticated chess and Go programs ever, which start the zero means it started with zero knowledge. So it effectively learns how to play chess, just like the picture I showed earlier, where you've taught the rules, so the software knows the rules of how the piece moves. And then it goes into an algorithm that just starts playing until it gets, within 24 hours, if I remember from the paper, it gets better than anyone that's ever played. So I'll come back as I have time to show you some of these highlights, but I'm going to sort of forge ahead now to talk a little bit about what networks are. So I've been extolling the virtues and telling you how great they are and they're revolutionizing everything, but what am I talking about really? How do they work? So this is what we call, particular exercise we're going to do today is part of the category we call supervised learning. So supervised learning is a subset of the problems we face in machine learning. And the supervised means that the data has labels associated with it. Or another way of thinking about it is we know the right answers for the training data. And so in the past, with the classical approach to software development, we would take the data and we would formulate rules. We would think of an algorithm to turn out from that data to the right answers. And what we're doing now is we're the data and the answers, the training data and the labels, putting it into a system which spits out the rules. So you can think of it as it's figuring out how to label this data. But the key thing is that we have the labels for a set of known pieces of information. This is a view of it. It's grossly oversimplified. So this, if you were seeing this, you would be pictures of cats and dogs. And for some reason, cats and dogs are always find their way into machine learning talks. But you would see that we take the pixels, the values for the representation of the image, and feed it into a network of layers. And these layers are kind of, you can think of them as doing mathematical functions to extract the meaning or the representation of that image. And they sort of feed this data up hierarchically into ever smaller layers. And then at the top, we've got it down to 2 nodes, which will either say it's a cat or a dog. The first to understand is the concept of a tensor. Does anybody here know what a tensor is? I have a sense. Okay, a few people do. So tensors are collections of numbers, and they can be in any. So to think of the simplest case, a 0 dimension, or we often call it a rank. A 0 rank tensor is just a number. We call it a scalar. And we'll use that as just a number we want to constant in a mathematical expression. A one-dimensional tensor is a list of numbers. So you can think of it as an array or a vector. And this is typically used in machine learning for feature representation. So if you I took a poll and I asked you, how old are you and where are you from? Thank you. I don't know, some information about you. I would have a bunch of numbers corresponding to your response as a feature vector. And that vector I could do some calculations on to come up with some guess about something I was trying to predict about you. A rank 2 tensor would be those vectors. And that would be a representation of all of you. Right now I would have a set of information that represented all of those features for everyone in this room. A rank 3 could be a three-dimensional object with a grid of numbers and then another dimension for a collection of such grids. And this is typically used for images. Is an image represented with a three-dimensional object because images are two-dimensional, and the reason is that each value in the image is typically encoded with a number. If it's a black and white image, it might be a grayscale number, where it is on the black and white spectrum. If it's a color, it might be hue and intensity and that sort of thing, or red, green, blue. But at any rate, these three-dimensional objects are typically used for images. And four-dimensional, or rank 3 tensors are used for video processing, because you can sort of think of a video as a sequence of images. So these tensors are really important to understand because they're the basic building block for creating these networks. And when we get into the lab this afternoon, we'll actually start manipulating tensors. So there's a note. Find out more on the previous slide, find out more about tensors and play around with them. Another reason I like to talk about tensors is it's right in the name of Tensor Flow. What Tensor Flow does is what Tensor Flow is, I should say, source software package that Google has made available externally. It's now kind of a community-based facility, and it's become one of the build these deep learning networks. It's not just for deep learning, it's really, you can think of it as a graph theoretic or a graph computational framework. And the idea is that you create these tensors and the tensors kind of flow through these computation graphs, and that's where the name Tensor Flow comes from. It's been around for a few years, it's gotten a lot of uptake. It's not the only library out there. There are a bunch of really good machine learning libraries, but this is the one that's become the standard in and has also achieved quite a bit of adoption in the industry in general. One thing about TensorFlow that I struggled with when I first was that it was a little bit hard to grasp and to use. I think it's gotten better quite a bit since TensorFlow 2.0 came out. But one of the things that really makes it easier for me to understand what I'm doing is that there's layer on top of it called Keras. Now, Keras was actually conceived as an abstraction layer that can work with multiple different machine learning engines. So not just TensorFlow, but other implementations of the core, if you will. But it's now been combined with TensorFlow. So there's a version of Keras that ships with TensorFlow and is very well integrated and has been tested and well exercised with TensorFlow. So if you're new to machine learning, I really suggest trying to use Keras with TensorFlow because it gives you this much nicer, higher level abstraction layer. And as we'll see in the lab this afternoon, building a neural network, a deep learning network with Keras, feels a little bit like using Lego. You kind of snap these blocks together for the different layers in the network. It's very intuitive, so I highly recommend that. The problem we're going to tackle this afternoon is classifying handwritten digits. This is a sort of the canonical machine learning problem for. It goes back to, I think, the 80s, maybe earlier. It was driven by the US Postal Service's desire to be able to automatically scan and classify handwritten, which is the US version of postal codes. And what we're going to actually do is build a network, and we can think of it as this green. Imagine we have a collection of these handwritten digits. What do they look like? They're files with digital representations of these squiggle digits. So imagine a piece of paper in 8, and we scan it into a computer, and we have a file. They're small, 28 by 28. And imagine that you were challenged to write a program that would read a bunch of these digits and tell you that that's a 5, that's a 7, etc. How would you do that? So the way we do it with neural networks is we're going to start with the very simplest possible neural network. And that would have one input layer and one output layer. And that's it. So what's the input layer? Well, I told you that these are 28 by 28 bit images. And let's assume they're black and white. So each value in the 28 grid is a number, let's say, between 0 and 255 that represents where it is between complete white and complete black. So we'll want to digitize that. And so we're going to take the grid and stretch it out into a big long vector. So 784 numbers, basically, in a big list. So the first layer of the network is going to be 784 nodes that are all just getting in one value. Each node corresponds to one pixel in that image. Now what do we do with all those numbers? We're going to feed those to the next layer. Now how big should the next layer be? This is where we're going to get the answers from. And the answer should be, it's a 0, it's a 1, it's a 2, all the way through 9. So we're going to have 10 nodes there. And the other thing is, these nodes are not just, emphatically, it's a 3. They're going to say the probability of it being a 3 is 0.675. So every one of these output nodes, you can think of as a probability generator. They're going to tell us the probability that the input scan corresponds to the digit they're responsible for identifying. Okay? So the top layer is the stretch of these digits, and the bottom layer is a probability function that tells us the likelihood of that input being a given digit. What's in the middle? What do we put between these things? We somehow have 784 numbers and condense them down to 10 numbers, right? So we're going to connect these input nodes to the output nodes. We don't have anything in the middle, so we have to. So the simplest thing we can do is connect all 784 input nodes to each output node. So imagine the first thing we're going to do is send them all to the 0 node. We're also going to send them to the 1 node and the 2 through the 9. So we have this like densely connected sort of mesh network, and all these numbers are coming in. Now you can imagine the one, let's say the node the output node that's responsible for finding ones, fixated, very interested in the middle region of the image, right? Doesn't care that much about stuff in the corner, because typically ones are kind of somewhere central. And so what it wants to do is your emphasis on the areas of the image that tend to convey a 1. Well, how do we do that? When we calculate the numbers that these output nodes are going to produce, we can put it on different parts of the input. And that's exactly what we do. We assign a weight to every one of these arcs. How many connections are there? 7840, because there's 784 on one side, and each of them is connected up to 10 output nodes. So we're going to have to come up with 7,840 weights. And by fine-tuning those weights, we can help the output nodes figure out what they're looking at. Okay? Now, if I said to you, here's a box, here's a black box, and you know what's inside it is all these connections, but it's got 7,840 dials on it. To set those dials so that this thing takes these inputs and gives me good answers on the output side. Two things would probably occur to you. First of all, you're going to have to try a lot of tests. You're not going to just put and go, yep, my job is done. You're going to do thousands and thousands of trials and keep messing with those dials until you get it working good. And that's what we call the training process. We put a lot of data in. We know the labels, so we can tell how far away wrong the answers are. And we actually make an entire set of data. The second thing that would occur to you is that that's a job you don't want to do, right? Nobody would want to figure out how to turn those dials. Even start. And this is what computers are good at. This is a mathematical problem. It's an optimization problem. And that's exactly what machine learning is all about. It's applying optimization, numerical optimization, to the things that we typically in the past would have tried to solve algorithmically. So what we're going to do is, this is what the image looks like to the computer. We're going to take these input values, here are all the weights, and we're going to multiply the weights by the input values, sum them together, and get an output value. So that thing on the right is like one output node. That's the responsible for finding a 4. Now, how we do this mechanically is we use something called matrix algebra. So you can think of the thing on the left as a stack of 100 images. Okay, so it's 100 tall. And it's 784 numbers wide, because each one of those images has, this stretched out list of values. And the thing on the top is the weight matrix. Those are our 7,840 weights, the current values of those weights. And we're going to multiply those things together. And for people who haven't done matrix multiplication, this is roughly the process. Take the row, multiply it by the column, and you multiply it by component-wise multiplication and then summing them. And all of this is not that important to know, but just so you understand what's going on, we're multiplying this matrix, and then we add something called a bias vector. And the bias gives us another degree of freedom. But the interesting thing about it is it stays fixed. It's one bias values for the entire, one set of 10 bias values for the entire model. It doesn't vary the way the weights do across the images. So bottom line is we're doing matrix algebra. That's what's going on inside this neuron. We set it up, we give it a bunch of training values and labels, and we have it iterate until it gets those weights set to a value where it does a very good job on the training data. And we hope it the data it has never seen before. We apply another function as well called an activation function, and in this case the activation function we're using is forcing this output to be a well-defined probability distribution. The characteristics of a good probability distribution are the values are between 0 and 1, and the sum of all the values sum to 1. So this softmax layer, it forces all the output values to be a well-behaved probability distribution. And it also has this tendency of sort of pulling the most likely probability out to stand out from the rest. You can see this visually, what it does. It's sort of, if you will. So it's math, and it's matrix algebra. And the good thing to know is you don't have to do that. Keras and Tensor Flow are for you. I just wanted you to have a sense of what's going on under the hood. So there's a couple more things to know about. There's something called a loss function, which I've glossed over. The idea behind that is, so you've got this network, math, and you're turning all these dials, and let's say you put a whole bunch of images in and you get a whole bunch of answers out. How do you know how it did? How do you know how your function is doing? Is it working well? Well, that's where the comes in. It's a mathematical way of stating how close was the answer. Now, it's pretty obvious how close it was when you have one example. But what we're doing here is running batches of images. Like I showed that stack of 100. Typically, we do 128 images for this kind of problem. And so we send a whole batch through, and the loss function is a mathematical way of saying, for that whole batch of 128 images, how close was the answer? How close was the answer? And by analyzing that loss function, we can use something called gradient descent, which is kind of roughly illustrated here. But what you can think of gradient descent doing, a mathematical function, and figuring out how to optimize it. So, think of in 2 dimensions that you have a curve like this, and it's a way to start at any arbitrary place on that graph and move towards the lowest value. The loss to be as small as it can possibly be for all of the images in the batch that we've just done. So we're optimizing for that one batch, and then we're going to do another batch and optimize for the next batch. But the point is we're using mathematical optimization to find how to turn those dials. That's really the magical part here. And again, you don't need to know how it works. You don't need to ever do it by hand, but I just want you to know what's happening. This is a graphical way of thinking about this optimization, which I want to show you very quickly. So this is a notebook I put together on a site called Observables. You can modify what's called the order, and you can change the constants. And as you do that, you're probably seeing, hopefully, the graph of the resulting function is moving around as it should. And once you're happy with the polynomial you've chosen, you click Generate. You can click it multiple times, and this will generate a random function with the same order. And then you can say Learn. And you see what happens. In fact, if I turn the iterations down to 1, reset this, generate, and then I click Learn, it'll do 1 iteration. So on the randomly generated curve, I should maybe blow this up. And with each step, you see it sort of moving closer and closer to the target curve. Now this is not there's no images or anything like that here. So this is really kind of like an analogy of what we're doing with neural networks. But in this case, finding these coefficients are kind of equivalent to finding the dials on this black box I referred to, finding the weights in that matrix. And the way it's finding them is very similar to what it does, the gradient descent I mentioned earlier. It starts with a completely random, and then by analyzing the loss, which in this case is the difference between the curve that it's currently looking at and the target curve, it figures out how to move those numbers to get closer and closer. So think of this image when you're saying that their neural network converged to the right function. So I said I would show you a couple of the ways Google's using these technologies, and I'll show you a couple of these. Like this is interactive. This isn't actually a Google thing, it's more of just an industry thing, but it shows another machine learning technique that's often used, which has to do with decision trees. So we define these kind of flowcharts. Data's coming in, does it satisfy this criteria or that, and it sort of flows through the tree like this. And then there's an animation here that shows the data coming through it, and it gets 100%. That's because it's the data that we used to formulate the tree. So effectively, looking at how accurate that is like asking, how accurate is my neural network if I run it on the training data I used to create the network? It's not a good measure of accuracy because the whole point of the process was to make it accurate for that training data. The really interesting question is what happens when it looks at data it hasn't seen before, and this is animated step where it shows 89.7%. So you can see some greens over here. This is a real estate model where green is San Francisco and blue is New York, I think. So you see it's percent accurate. And that's not as good, but it's more realistic. Typically, you wouldn't expect it to be perfect with data it's not seen before, but you want it to be as good as possible. This one's fun. It's a example of reinforcement learning. So somebody at the DeepMind team did this to try to teach some software how to run this game called, we call it Breakout in the US. I'm not sure if there's a different, but initially, it's pretty awful. Starts to get a little bit better, but still not so great. After 400 training episodes, it's actually quite good. Jittery, which is probably an artifact of the mechanisms, but it's now kind of comparable to probably a pretty good human. And then after 600 iterations of the training, quite interesting happens. It figures out that if it can knock the edges of the grid away, then it can score. The ball just kind of goes crazy in the back of the grid. No one taught it that. No one put an algorithm that said, you know, if do this, then that. It just found it. And this is an interesting property of these sort of algorithms, is they discover things that just the way humans discover things. One last thing I'll mention is there was some interesting work done recently where people were able to apply these kind of neural networks, these deep learning networks, to retinal images of your eye. And they found that they were able to predict cardiovascular risk and some other medical conditions with a high degree of accuracy. And no one had ever even realized this could be done. This is a little bit like finding out, like a piece of software figuring out that it can beat breakout by breaking. Like the algorithm found something we didn't even know or realize could be a useful diagnostic technique. And if you think of the power of that, maybe like with mobile devices in third world countries, being able to diagnose vascular health by looking at their eyes, it's super powerful. I think I'll wrap it up here. Thank you for your attention.